Imagine a force so mysterious, so pervading, that it makes up around 68% of the universe. Yet we know almost nothing about it. Welcome to the enigma of dark energy. Dark energy, a term that sounds as if it's been plucked straight out of a science fiction novel, is actually a scientific concept that continues to baffle the brightest minds in cosmology. It's a form of energy, but not the kind we're familiar with. It's not the energy that lights up our cities, powers our cars, or even the one that fuels the stars. This energy is dark, unseen, and yet its effects are cosmic. To understand dark energy, it's important to distinguish it from its elusive counterpart, dark matter. Dark matter is a type of matter that, although invisible to our telescopes, exerts gravitational pull on galaxies and clusters. Dark energy, on the other hand, is a force that seems to be working against gravity, causing the universe to expand at an accelerating rate. The concept of dark energy was born out of a groundbreaking discovery made at the tail end of the 20th century. Astronomers studying distant supernovae found something entirely unexpected. The universe, they discovered, wasn't just expanding. Its expansion was speeding up. This was remarkable because, according to the then accepted theories, gravity should have been slowing this expansion down. The only way to reconcile these observations with our understanding of physics was to propose a new form of energy, an energy that permeates all of space, pushing galaxies away from each other and causing the universe's expansion to accelerate. This energy, though undetected and unknown, was named dark energy. And so, the mystery of dark energy was born. It's a mystery that has persisted and deepened over the last 2 decades. Despite making up the majority of our universe, we still know very little about the true nature of dark energy. So, dark energy, unlike its cosmic cousin dark matter, is a force that appears to be causing the universe to expand at an accelerating rate. Now, you might be wondering, how do we even know dark energy exists? Well, the universe has been leaving us clues. Our first clue comes from distant supernovae, those spectacular stellar explosions that light up the cosmos. By observing these celestial fireworks, scientists have made a startling discovery. The universe isn't just expanding, it's accelerating in its expansion. It's like throwing a ball up into the air, and instead of it slowing down and falling back, it speeds up, defying gravity. This unexpected acceleration hints at the presence of a mysterious force we now call dark energy. But supernovae aren't the only breadcrumbs in this cosmic trail. Let's talk about the cosmic microwave background, or CMB for short. This is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. By studying the CMB, scientists have found patterns that support the existence of dark energy. Moreover, these patterns have allowed us to estimate how much of the universe is made up of this enigmatic substance. Current estimates suggest that a whopping 70% of the universe's energy content is dark energy. Moving on, let's delve into the large-scale structure of the universe. You see, the universe isn't a random jumble of galaxies. Instead, it's a vast cosmic web, with galaxies clustered along filaments separated by vast voids. By surveying this cosmic architecture, scientists have found more evidence for dark energy. The distribution and clustering of galaxies, their movement and the vast cosmic voids all point towards an invisible force driving the universe apart. Finally, we come to gravitational lensing. This is a fascinating phenomenon where gravity bends light, acting like a lens. It's one of the predictions of Einstein's theory of general relativity and has been observed countless times. But what does this have to do with dark energy? Well, gravitational lensing allows us to map the distribution of dark matter. And since dark matter and dark energy are intertwined in the cosmic ballet, understanding one can help us constrain the properties of the other. So there you have it. From the distant supernovae that defy our expectations, to the ancient light of the CMB, the intricate cosmic web of galaxies, and the lensing power of gravity, these are the clues that lead us to the concept of dark energy. From supernovae to the CMB, to the large-scale structure of the universe, the evidence for dark energy is compelling. We've established that dark energy exists, but what do we actually know about it? Well, one way we attempt to understand dark energy is through parameters like its energy density and equation of state. Energy density is a measure of how much energy dark energy contributes to the universe's total energy budget. Now, if you're picturing a cosmic accountant frantically crunching numbers, you're not far off. As it turns out, dark energy accounts for about 70% of the total energy in the universe. That's more than all the stars, galaxies, and other forms of matter combined. The equation of state, on the other hand, describes how dark energy behaves over time. It's a bit like a personality profile for dark energy, if you will. This equation involves the ratio of dark energy's pressure to its energy density. The value of this ratio tells us whether the density of dark energy changes as the universe expands. So we have a few numbers, a few equations, but what does it all mean? Is dark energy just a cosmological constant, or could it be something else altogether? The cosmological constant, represented by the Greek letter lambda, is one of the simplest models for dark energy. It suggests that dark energy has a constant density, which means its value doesn't change over time or space. It's the steady, unchanging character in our cosmic drama. But there are other theories too, like quintessence or phantom energy. Quintessence models propose that dark energy's density changes over time. Think of it as the unpredictable, capricious character, always keeping us on our toes. Phantom energy, on the other hand, is even more exotic. It suggests that dark energy's density could increase over time, leading to a big rip scenario where the universe ultimately tears itself apart. One of the most intriguing properties of dark energy is its negative pressure. Yes, you heard right, negative pressure. This is a bit of a head-scratcher because in our everyday experience, pressure is always positive. But in the realm of cosmology, things can get a little weird. This negative pressure is what leads to the anti-gravity effect of dark energy, causing the universe to expand at an accelerating rate. So, while we might not know exactly what dark energy is, we've certainly managed to learn quite a bit about its properties. It's like getting to know a mysterious stranger. You might not know their name or where they come from, but you learn about their quirks, their habits, and their influence on the world around them. Dark energy, with its negative pressure and anti-gravity properties, remains a fascinating puzzle in the cosmic jigsaw. But as with any puzzle, each piece we discover brings us one step closer to seeing the full picture. Dark energy is a mystery that continues to baffle the brightest minds in cosmology today. This elusive force, seemingly embedded within the fabric of the cosmos, is believed to be driving the accelerated expansion of our universe. But what exactly is dark energy? Is it a new form of energy entirely, or perhaps a property of space itself? Or could it be a sign that our understanding of gravity needs revision? Various theories propose different answers to these questions. One of the leading theories is the cosmological constant model, which suggests that dark energy is a static property of space. It posits that empty space is not truly empty, but filled with temporary virtual particles that contribute to the energy of space. This energy, in turn, could be responsible for the universe's accelerated expansion. But the cosmological constant model is not without its challenges. For one, it predicts an energy density for the universe that's a whopping 120 orders of magnitude larger than what we observe. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved issues in theoretical physics. Another possible explanation for dark energy is quintessence, a dynamic, time-evolving and spatially dependent form of energy with negative pressure. Unlike the cosmological constant model, quintessence isn't constant and can change over time. It's like a field spread throughout space, somewhat similar to the fields associated with fundamental particles. On the even more speculative side, some suggest that dark energy could be a sign of extra dimensions. In these theories, our familiar three-dimensional universe is embedded within a larger, multidimensional reality. Gravity, seeping into these extra dimensions, could appear to us as dark energy. While these theories are intriguing, none provides a definitive answer. They remain hypothetical, awaiting confirmation or refutation from empirical evidence. This is where future research comes in, with upcoming experiments and telescopes designed to probe the nature of dark energy. Projects like the Dark Energy Spectroscopic Instrument, or DESI, aim to create a three-dimensional map of the universe, tracking the distribution of galaxies to reveal the influence of dark energy over time. The Euclid Space Telescope, set to launch in the mid-20s, will survey the cosmos, studying the large-scale structure of the universe and the distortion of light by gravity to better understand the dark universe. Finally, let's consider the implications of dark energy for the fate of the universe. If dark energy remains constant or increases over time, the universe's expansion will continue to accelerate. Galaxies will move farther apart, and eventually the stars will burn out, leaving a cold, dark universe, a scenario known as the Big Freeze. On the other hand, if dark energy decreases over time, the universe's expansion could slow down, stop, or even reverse, leading to a big crunch. In the most extreme scenario, if dark energy increases rapidly, it could rip apart galaxies, stars, planets, and even atoms, a hypothetical event called the Big Rip. In conclusion, dark energy, this enigmatic component of our universe, presents many unanswered questions. Its nature, its properties, and its implications for the fate of the universe are subjects of intense research. While we may not have all the answers yet, the quest to understand dark energy continues to shape the future of cosmology. So where does this leave us in our understanding of dark energy? We've journeyed through the cosmos, unraveling the mystery of dark energy, this elusive entity that makes up about 70% of our universe's energy budget. We've seen how it differs from dark matter, its silent partner in the cosmic ballet, and how it remains largely unknown despite its pervasive presence. We've revisited history, noting the discovery of the universe's accelerating expansion, a finding that led scientists to propose the existence of dark energy. We've also examined the evidence that supports its existence. The distant supernova revealing an accelerating expansion, the cosmic microwave background measurements, the large-scale structure of the universe, and the phenomenon of gravitational lensing. We've explored the properties of dark energy, its energy density and equation of state. We've dived into theories whether it's a cosmological constant or something else entirely. We've also touched upon its intriguing characteristic of negative pressure, which results in anti-gravity, a feature that could be responsible for the accelerating expansion of our universe. We've pondered over the open questions and future directions of research. What is the physical nature of dark energy? Can we directly detect it? And what would its properties mean for the fate of our universe? But as we've seen, despite the wealth of observational evidence and theoretical models, the true nature of dark energy remains veiled in mystery. Its existence is inferred, its properties are theorized, but its essence is yet to be captured and understood. This mystery is what drives scientists to continue their investigations. Upcoming experiments and telescopes are on the horizon, each with the potential to bring us closer to understanding dark energy. But until then, the enigma of dark energy continues to fascinate us, reminding us of how much we've learned about our universe and how much more there is to discover. As we delve deeper into the universe's mysteries, the true nature of dark energy continues to be one of the greatest puzzles awaiting our discovery.